Radboud Universiteit.
Usually in physics, when you encounter infinity, that's sort of a warning that something is wrong with the theory.
Welkom bij een speciale podcastreeks van Radboud Science Snacks en Radboud Reflex. In deze serie kun je luisteren naar gesprekken met Radboud-wetenschappers die zijn opgenomen tijdens wetenschapsfestival Oneindig in Nijmegen. Er was een live publiek en het gesprek was in een galmende kerk, dus het zou kunnen dat je dat hoort. Dit keer, in het Engels, wiskundige Walter van Suijlekom over oneindige vormen.
So, Walter, I imagine that the concept of infinity comes up quite a lot in your work. So when you hear the word infinity, what does it mean for you? What kind of image does it conjure up?
So actually it's about not bounding yourself to something that you have in your mind, to something you want to be completely open to what you want to explore, both mathematically but also physically. And so, for instance, if you think about numbers, you don't want to restrict yourself to counting up to, as you just said, up to 100 or 200 or maybe a million or whatever number you imagine. You want to be completely free and want to say something about all numbers. And that's where actually you don't want to bound yourself. You want to be completely free in saying something about all the numbers.
Right. So
that's one example.
Okay, so it's about not bounding yourself. Because when I think of infinity, I'm sort of, for instance, that example that I gave, I think about basically counting from 1 to a million and then on, and at one point, sort of, you lose count and then you think this is infinity, but it's a bit different for you.
Yeah, it's more like, so for instance, if you think about numbers, there's always this issue that whenever you give a number, you can always take another one, the next one, say, so you just add one. And you can keep doing that. Whatever big number you give, there's always a number which is higher.
Yeah.
And that is actually something you want to capture. And this you do by not sort of grasping or defining infinity, but it's more about allowing yourself to have infinitely many numbers you can work with.
Yeah, because I can imagine it's kind of difficult to sort of define the concept of infinity, to actually define what it is.
Yeah, so it's more like a way of viewing. Actually, it's more of a starting point.
Yeah.
That you want to start like that. This is what we set, actually literally. We start with that infinite set of numbers.
Yeah.
You want to say something about all those numbers.
Yeah. You say it like it's something that is very, like, comes up in your work. It's very normal. But when I hear you start with an infinite set, that for me that sounds outrageous.
So let's give maybe a nice example, which is it's a hotel. This is Hilbert's hotel or Paradox, and so what you do is you start with the hotel. Say you have like 20 rooms, and they're all full, so every room is occupied. There comes this person in front of the hotel, and he wants to book a room, and then okay, sorry, there's no room because I'm completely full. Now, what Hilbert's hotel actually does, that's a kind of a different hotel, and it's a hotel with infinitely many rooms. So it just means that there is no bound on the numbers of the hotel rooms. So you have room number 1, number 2, 3, 4, 5. It doesn't stop at 20; it just keeps going. So any number is a room. Now that hotel is also full. So that you may say, okay, the person in front of the hotel is you have to disappoint him. He cannot get a room. However, what you can do in this hotel is you just go to the person in room number 1. You ask him to move one room to 2. The person in number 2, you ask, please go to number 3, 3 to 4, 4 to 5, 5 to 6, and so on. You just ask everyone in the hotel, just move up one room.
Yeah.
Everyone can do it. That instruction is completely clear.
It's
you just
easy,
move to the next one, no matter how big the number is. And then you have a free room, because number 1 is now free.
Yeah.
The person can come in.
Yeah, so what you do is, so I don't know anything about mathematics, but you add 1 to infinity.
Essentially, yes.
Yeah.
If you want to say it like this, but more formally, it's about this kind of possibility to just keep shifting, even by 2. So you can allow 2 people to enter. And in fact, it's even worse. So if I may, so you can actually, so suppose you have this hotel, it's again full, infinitely many rooms, they're all full. And there comes a bus with infinitely many people in the bus. Okay, so they arrive. And then, okay, you have a problem because you may say, well, this will never work. I can never put these people in these rooms. But now you ask everyone in the hotel to move kind of to the double room number. So the person in number 1 goes to 2. The number in 2 should go to 4. The number in 3 should go to 6, and so on. So you just double the room number. They all shift. So now you have a hotel which is occupied in the even room numbers.
Yeah.
But all the odd ones are free. And this is actually also infinitely many. And so you can allow for infinitely many from this bus to also enter. And this is sort of the strange thing about infinity.
Yeah.
Actually, you can capture it like this.
But you can capture it mathematically because it.
Exactly.
Yeah. Because it still sounds weird. That's obviously why it's a paradox.
Exactly. It looks like a paradox, but actually it's perfectly well defined.
Yeah, and it works.
Mathematics.
Yeah. So I did a bit of research, obviously, to prepare this conversation, and I read that there are even more kinds of infinity than one. Can you elaborate on that?
Yeah. So you're probably all familiar with the fact that you don't just count like from 1, 2, 3, and so on, but you may also use decimals. And there's another type of infinity because you could write a number with infinitely many decimals. So between 0 and 1 actually also lie infinitely many numbers. So, and this is adding to infinity that we already have by counting these numbers. Also between 0 and 1 you have infinitely many numbers. So that's sort of adding to infinity. It's sort of a different level of infinity. We can also define that in mathematics. So you have these two notions and they're actually different.
Yeah.
Different types of infinity.
Yeah. So the first one is counting.
Countable. It's even called countable.
It's called countable.
So perfect.
Yeah. And the other one is what's it called?
Well, so that's for instance what you get with the real numbers.
Yeah.
But that's not countable in that sense. So.
Yeah. Yeah. So a real number is.
That's a technical term for the decimals.
Oh, right. Yeah.
The decimals.
Yeah. Okay. And so I also read that one of those two infinities is bigger than the other.
Mm-hmm.
So what does that mean? How can one? Because infinity means no end, goes on forever and ever. How can one infinity? So of the two that you just described, how can one be bigger than the other?
It's about so for instance what I just said about the even numbers. So actually there you can say there's essentially as many even numbers as there are odd numbers.
Yeah.
There are also as many as there are numbers. So even though it looks like you have like half the size, if you take even
this
numbers,
sounds
that's very strange. But
sounds
what is an
strange.
even number? It's just 2 times any other number. So in that sense, it's just the same number of even numbers as you have numbers.
Yeah.
So there you can actually, what you do is you say, well, take a number and you multiply it by 2, you get an even number. You can also go back by dividing by 2. So there's sort of a, what you call a 1-to-1 correspondence between all the numbers and the even numbers. And the same with the odd numbers. If you add decimals, you cannot do that. And this you can prove that you have actually more overcountable numbers with decimals than you have if you just count them.
Right.
And that's the different level I was talking about.
Yeah. I sort of understand and I sort of don't. But I think
but it's okay.
Yeah.
It's the mystery of infinity.
Right. So does this concept of infinity, does it have any does it exist in the real world? Does it have any bearing on reality?
Yeah, so already in counting, I would say, you don't want to sort of build a world if you do computations where you say, well, I can only do up to 1 billion. So you don't want to restrict yourself.
Yeah.
Actually, you find that that in nature also you don't say, well, at some distance the world ceases to exist or something like this. There's, as you said in the introduction, there's not a bound on the universe.
Yeah.
Or you don't want to put a bound yourself. I mean, there may be one physically, but you don't want to kind of restrict yourself in modeling by saying, well, up to there I can compute, and then okay, I don't do it anymore. So
can you elaborate on that distance? So there might be a bound to the universe, but you don't want to restrict yourself?
You in the model with which you describe the universe, you sort of want to stretch this out. But as we also know, the universe started at some point.
Yeah.
with the Big Bang, and then it's sort of expanding, and then we also know that there's actually a certain size corresponding to that, just because it happened some time ago, not infinitely long ago.
Yeah.
It's a finite time ago, so something happened and brought this matter or this radiation there. But in the model itself, we sort of want to describe this by not bounding ourselves because of some mathematical principle.
Yeah.
There we want the mathematics to be completely allowing any number to exist.
Yeah. But then does that also mean, so you use infinity because you don't want to bound yourself? But does something like infinity also really exist in the real world? Is there infinity in the real world? Not just to describe something where we don't want to limit ourselves, but for instance, the universe, can it actually be infinite, or other examples of infinity in the real world, in the natural world?
So that's a good question philosophically. I mean, so as I just said, the universe itself, we
Is a contender.
assume it's bounded in size, just because it started some time ago with some velocity. It was expanding, so it's not supposed to be infinite in that sense. In really modeling, we don't want to put that restriction, and that's also going in the other direction, maybe in the infinitely small.
Yeah.
Also there, if you do modeling, you don't want to sort of restrict yourself, even though physically there may be such a stop where you say, well, that's sort of the smallest you can reach. And there's, of course, theories about that.
Yeah.
But the theories themselves, they're based on what we call the continuum. So actually infinitely small.
Yeah. Yeah. So we're talking about so atoms, quantum mechanics. So there's. So can you elaborate a bit on what you just said? Is that, how does the concept of infinity there have a role there?
Yeah, so that's essentially by describing the way we describe, for instance, space around us. It's suppose think about the Earth, the shell, say so
Yeah.
So you want to describe that mathematically as what we call a sphere, so it's the edge of a ball.
Yeah.
And there you don't want to sort of restrict the description to stop at some point, at some small scale. That's actually much better described by these decimals. So you can actually zoom in and you describe something which is continuous.
Yeah.
And not discrete. So you don't want to sort of put this together in a discrete way.
Yeah.
This mathematically you want to describe as a continuum.
Yeah. Yeah. So I'm just trying to sort of really grasp this. So you have this the Earth, and when you try to you want it to be actually like a very smooth curve and not like consisting of tiny bits in the end. Or
Exactly. Yeah.
Yeah. Yeah. And do we know anything about whether that's really true?
Of course, in physics that's a different question. So what I was saying is about the mathematical modeling that we do to describe this. But of course, we also know that things are built from smaller parts.
Yeah.
The Earth, and if you zoom in, you may go to atoms.
Yeah.
You may even try to go even deeper into that. So there is some kind of length scale which is sort of fundamental in physics, where that stops that description.
Yeah. So you cannot infinitely zoom in.
That's right.
Yeah.
And also because you need infinite amount of energy to zoom in at an infinitely small scale.
But what do you mean?
So if
Infinite
you
amount of
wanna-
energy?
So for instance, if you, you may think about these, so with a microscope you could zoom in.
Yeah.
If you want to zoom into atoms, you have to use something else because, I mean, light and atoms, they actually interact. So you have to, if you want to zoom into matter, you have to build like particle colliders, which use a lot of energy. Actually, the zooming in is like inverse to the energy you need. So if you want to zoom into a very small scale, you need much more energies.
Okay.
And also that is limited, just in practice it's limited.
Yeah.
You have an infinite amount of energy. So you can also not zoom in that much.
Yeah.
So, and that's a length scale which is fundamental in physics, where things stop. And then you have to come up with another theory.
Yeah.
That's
Right.
the challenge.
And are there other examples of infinity in nature? For instance, I'm thinking about black holes, which are sometimes described. So yeah, maybe you can describe them better than I probably can. Which are described as infinitely dense sometimes.
Yeah, so that's so indeed there you have the phenomenon that the the energy or the mass is concentrated in a single point, the singularity of the black hole, and there you have a type of infinity, which actually we don't really go there, or it's even fortunately maybe it's shielded by an event horizon, but the effect of that we can.
What is the event horizon?
That's the point of no escape, where also light cannot escape.
Right. So if something falls in, you cannot get back.
It's quite far away from the singularity.
Okay.
That's fortunate in a sense. Also, still.
But does it? Maybe this isn't a tricky question, but can you describe the distance between the sort of the singularity and the event horizon?
Yeah, that's related to the mass, which is in there. So it's
not infinite.
No.
Okay.
That size is just around, and what we see, for instance, in these images of the shadow of the black hole, this is still a bit further, not so far away, and so what we describe, allowing us this singularity, so this infinite point, infinite density, we only sort of see in physics the effect it has in the surroundings.
Okay.
So in that sense, you do not really see the infinity or the singularity, but it does play a crucial role in the description of black holes.
Yeah. So there's sort of a returning thing that infinity plays a role in the description of a lot of natural things in the universe, atoms, but we don't necessarily say that these things are actually that infinity is real in that sense. It's just we use it to describe these things because it doesn't really matter.
Yeah, so we allow this to be let me say it like this. So if usually in physics, when you encounter infinity, that's sort of a warning that something is wrong with the theory.
Okay.
So you have to sort of do something about it, either by what I just said, so you don't really see this physically, or there's some other mechanism. So in the theory, you want to sort of change it or interpret it better.
Can you give an example of that where infinity comes out and you this is something that you do not want?
Yeah, so a famous, so very technical, so I won't go into that,
Okay.
Of course, but it's what is in quantum theory, what people encountered is that they did computations in the 50s, in the 60s, and every time they did a computation, infinity came about. And so they didn't know what to do with that. So what you have to do actually is understand this infinity and have a very clever mechanism to subtract it and to redo the computation. And then you find something which is actually finite, and you can check it physically. So this is the work of 't Hooft and Feldman, so our Nobel Prize winners in physics some time ago. And so that's really where you encounter infinity in the theory, and it's a warning saying, okay, you have to do something better and do the computation again.
Yeah.
So re-normalize, so redo the computation, and then you find something which actually works.
Yeah. And why is it a warning sign? Because what does it mean, for instance, if a formula pours out infinity? What does that mean?
So if you want to measure that, you have a problem.
Because it's
How
not
are you going to
measurable.
measure infinity?
Right.
So you can measure numbers, energy, in whatever unit you want. You can measure energy levels, but if it's infinity, you will not be able to measure it.
All right. Yeah. So is infinity for you as a mathematician? Because we've been talking about infinity now for a while, and for me, it's something that really wrecks my brain to think about this concept. Is it for you? Does it still fascinate you? Does it irritate you, or are you kind of like, it's just something that I work with every day?
And it's actually very useful. So I put it to the opposite. So it's a starting point, as I said. And so we work with it.
Yeah.
It's this freedom to talk about, say, all numbers at the same time. This is what is the positive thing about that.
Yeah.
So we actually turn it into something which is asset. So something which is a nice feature.
Yeah. So
not being afraid of that.
It's nice. It's nice to see infinity.
Yeah.
In your work.
Then you have the complete possibilities, completely flexible, no limitations.
Yeah. Perfect.
Radboud Universiteit.